let's look a little further into these compression indices, C sub C and C sub R, and also the maximum past pressure, sigma P prime. Talked briefly about those in the previous video, but I think they're worth exploring a little bit more deeply so that you can understand where they really come from. What I'll do is use a axially loaded bar as an analogy for what's happening to the soil, because I think it really does lend itself to an easier interpretation of what's going on. So let's say that we have, this bar in tension, and we just measure a stress-strain curve. So here we have axial stress on the y-axis and then axial strain on the x-axis. Well, we know that the initial slope here is going to be along the Young's modulus, right? If we were to measure the Young's modulus, we could put some stress on that bar, measure the strain, and the slope of it is E. But then no material has an infinite capacity, right? It can't just keep going along this E line forever. Eventually it will reach its yield stress. So maybe that's 60 KSI if it's normal steel or something like that. All right, and a lot of material, after it reaches yield, sometimes it just goes flat, like it can't take any more stress. If you continue giving it strain, the stress will just stay the same. But some material does have a post-yield hardening. So let's just assume that this bar is a material that has some post-yield stiffness. So we're going along E, then all of a sudden, boom, we hit the yield point, and now the slope is E sub Y. It's like a yield slope or elastoplastic slope. All right, so let's take a look at these first two bullet points that I've written down here. So initially during loading, the slope is E. Once we reach the yield point, the slope becomes EY. Now let's think about what would happen if we were to go to this point right there and then unload the bar. So we've been putting tensile strain, now we reverse it and start putting compressive strain. What will happen, maybe I'll draw this in blue so that it's clear that it's being added on. It's going to unload along the Young's modulus slope. So this is going to be a slope of E. All right, so we're unloading. Then let's say that we were to reload. We come down to some point and we go back up. It will go along the slope E again until it reaches the maximum pressure that was imposed on it before we started unloading it. Then it will turn this corner and again start going along the E sub Y line. So I'm going to call this point right here, let's call this one, this is not a yield. Remember, so we've gone beyond the yield stress now. Let me erase that, I'm going to put it up here. Because of this post-yield stiffness, we've actually been able to go beyond sigma Y. This material can actually take more than sigma Y, and we've gone to something that I'll call like a sigma max. But of course, sigma max is not a single number, right? Once we've come and unloaded and then reloaded, we go past sigma max again. So now here's a new sigma max. It's way up there. So sigma max is not a constant. I'll write it in here. These are both sigma max. They're just sigma max at different times. This first sigma max is the one that existed only after we loaded up to this point, right? So during this whole unload reload phase, the maximum pressure that had ever been imposed on the material was sigma max. Once we load past sigma max again, now we've moved it. So sigma max is moved up here. Okay, so consolidation is very similar to this idea, except instead of talking about axial stress and axial strain, we're now talking about volumetric strain. And in the case of one-dimensional consolidation, vertical stress. In the case of multidimensional consolidation, mean effective stress. How much is the overall mean stress changing? We'll stick with one-dimensional consolidation here, so you can think of it as vertical stress. So when we do consolidation, C sub C, which is the version compression index, that's analogous to E sub Y, the elastoplastic slope. So basically when the material is yielding, it has kind of not a very big slope in terms of this change in stress with strain, right? It's accumulating a lot of strain per change in stress. Well, C sub C is also yielding, but it's yielding volumetrically. So you've now squeezed water permanently out of the clay. When you unload it, the clay doesn't rebound back to where it was before. You've permanently changed its void ratio. All right, C sub r is analogous to Young's modulus. So it is an elastic constant. And if you were to load here and then unload, the bar would go right back where it was. Similarly, if you were to load along the C sub r index and then unload, the clay would go right back to the volume that it was before. You would not change the volume permanently. Then sigma p prime, the maximum pass pressure, is analogous to sigma max. So sigma p prime is like this point here or that point here. And also at the very beginning of loading, sigma max was the yield stress, right? Because that's the point where it's going to start to change slope. So sigma p prime is a variable. It's not a material constant, right? If you load past the maximum pass pressure, or you reach the maximum pass pressure and continue loading, sigma p prime changes with it, right? So it's going to evolve during virgin loading. And what this means is that the soil really has a memory. It knows how much pressure has been placed on it in the past, and it will only start undergoing elastoplastic deformation or permanent deformation once it reaches that maximum pass pressure and gets loaded beyond that maximum pass pressure. So here we can draw, let me sketch in here, a little diagram. Okay, we're going to have E on the y-axis and then log sigma v prime on the x-axis. So a couple of things are different for consolidation than for axially loading the bar. Instead of strain, we tend to favor void ratio, right? But that's a measure of volume of the soil. And then instead of stress, we have log of stress, because that linearizes the relationship. And then we rotate the axes, right? So for the bar, we had our strain metric on the x-axis and the stress on the y-axis. Now the void ratio is basically related to strain, and then we have stress on the x-axis. So we kind of flip things around. And then if we had here's like a C sub r line, and then it would reach a maximum pass pressure and go down the C sub c slope. So here's CC. This one is CR. This one would be sigma p prime. So at the time, like if we started loading from right there, the maximum pressure that the soil's ever experienced would be right at the point where it makes that transition and starts loading on the virgin compression line. Now as you do load along here, sigma p prime is increasing, right? It's going to slide down as you move this way. And then this line where the soil is going on the elastoplastic line is called the normal consolidation line. I'll get to that in just a while. All right, now let's talk about Overconsolidation Ratio, or OCR. Basically, overconsolidation ratio is a measure of how big the maximum pass pressure is relative to the current vertical effective stress. So let's say that we have a site that has some clay here, and back during the Pleistocene, during the last ice age, maybe there was a glacier on this site. The glaciers could be pretty thick, a kilometer thick or something like that. So that puts a tremendous pressure on this clay, and it would consolidate the clay underneath all that weight to some pretty big maximum pass pressure. And then as time goes by, glaciers retreated, we're no longer in the ice age, so maybe today there's no glacier. Large portions of the sort of upper Midwest and Northeast United States have this condition. They were underneath glaciers, now they're not. This is called glacial till. So right now, the vertical effective stress is pretty small because that glacier is not there anymore pushing down on the clay. But sigma p prime remains big. It stays the same as this sigma p prime because the clay has a memory. It remembers its stress history. It still knows that that glacier was there, and its void ratio is pretty low. It's very highly consolidated. So we would say that this soil is over-consolidated because its current vertical effective stress is smaller than the maximum pass pressure. And if we were to go to that site and gather a sample of that clay, and do a consolidation test, we might find that we would get points like this, and then we would reach a point where we eventually are going beyond the maximum past pressure that was exerted by that glacier. And so by getting a sample of clay out of the ground and putting it in the consolidometer, we can actually figure out how much was the pressure that was exerted by that glacier. That's going to be sigma p prime right at the turning point of the consolidation curve. Okay, now here's a couple more definitions, and then I'll come back to this normal consolidation line thing. So if sigma v naught prime is less than sigma p prime, we say that the soil is over-consolidated. That means that it's experienced a bigger pressure in the past than what it's feeling right now. And let's take a look at what that means in terms of void ratio change. So let's say that we're starting here. We are having sigma v naught prime less than sigma p prime, so we're over-consolidated. It means that the slope that we go along until we reach the maximum past pressure is going to be the C sub r line. So I didn't label those here, but this one is C sub c, and this slope is C sub r. So we're going to go along C sub r. That's the elastic slope. So if we were to load and then unload, the clay would consolidate, and then it would heave, and the volume, there would be no permanent volume change, unless we went past this sigma p prime and started going down the C sub c line, and we're inducing permanent volume change in the soil. All right, if we do go past the maximum past pressure and start inducing elastoplastic deformation along the C sub c line, now the soil is normally consolidated. And that occurs when sigma v naught prime is equal to sigma p prime, right? So if we load it to right there, now all of a sudden the soil is normally consolidated, and that means we're going to start loading down this line. And you might be thinking, okay, how, you said that they're equal, but if we go past sigma p prime, isn't sigma v naught prime now bigger than sigma p prime? Right, here's sigma p prime. We're now past it. We're going down this line. Okay, remember, sigma p prime is not a constant. It's not a material constant. It's a variable. So as you load down the line right here, sigma p prime is increasing with you. It's always staying right where you are. That's why sigma v naught prime is equal to sigma p prime, because it's being updated. So it's impossible to have sigma v naught prime bigger than sigma p prime. And if we think about it, sigma p prime is defined as the maximum pressure the soil's ever been exposed to. What's the maximum past pressure that it's ever felt? Well, it can't currently be feeling a bigger pressure, sigma v naught prime, than the maximum pressure it's ever felt. It's either currently experiencing its maximum past pressure, or it's currently experiencing a pressure smaller than the maximum past pressure. So you can't have a stress now that's bigger than the stress that's ever been placed on the soil. Okay, so that line where OCR equals 1 is called the normal consolidation line, or NCL. And we have OCR equals 1, and we have sigma p prime is equal to sigma v prime on that line. All right, now the overconsolidation ratio is defined here. It's sigma p prime divided by sigma v prime. And OCR by definition has to be greater than or equal to 1. If it's equal to 1, the soil is normally consolidated. If it's greater than 1, the soil is overconsolidated. One thing I want to point out is that there is room for confusion here when we use the word consolidation or consolidated, especially when we start talking about overconsolidated or normally consolidated, because those mean something very specific in the context of soil mechanics, and they mean something else that's very specific in the context of geology. So geologists don't actually use the terms overconsolidated and normally consolidated. They use the terms consolidated and unconsolidated. And what they mean is not related at all to what we mean. So our definition in soil mechanics of overconsolidated and normally consolidated, totally different thing. I've seen people have misunderstandings about this, so I just want to mention it. So for geologists, consolidated sediment is sediment that has lithified into sedimentary rock. So it's a formational material, generally pretty old at this point to have had time to lithify. Unconsolidated sediment is not yet lithified into rock. It's loose sediment that's just there, like soil. So generally what we deal with in geotechnical engineering is unconsolidated sediment, and that unconsolidated sediment could be overconsolidated or it could be normally consolidated depending on its stress history. So just a little word of caution to be sure that you know these terms and you don't make a mistake. All right, let's look at causes of overconsolidation. We've already talked about one. Glaciation is an example of mechanical preloading. So if the glacier was here and then it's gone, or it's much thinner or something like that, it has put the clay under a high pressure in the past, and that high pressure is no longer there now. So it's been loaded to a big pressure in the past and then unloaded. That can also happen from landslides. So if you had soil and there was a bunch of soil on top, and that soil on top is subsequently removed due to a landslide, then the clay might become overconsolidated as a result of that. All right, another cause is groundwater fluctuation. So let's say that we have a condition here, number one, the groundwater table is pretty deep. Then the clay gets consolidated under the effective stress condition here for that deep groundwater table. Then in number two, the water table moves right up to the surface. All right, and what that does is reduces the effective stress in the clay, because now the pore pressure has gone up, right? The water table's gone up, so pore pressure has gone up. And then I'm going to assume the total stress has stayed the same, right? So the total unit weight's the same. So if we come over here to this stress diagram, we see that this black line is sigma V naught, that's the total stress. It's the same for both 1 and 2. The pore pressure here for 1 is pretty low, right? It's the groundwater table is deep, so the pore pressure is low. The water table is higher for 2, so you get more pore pressure. Therefore, since the total stress is the same and the pore pressure is different, the effective stresses are different too. So here is condition 1, the total stress and effective stress are the same above the water table, then they become different below the deep water table. So that's sigma V naught prime 1 right here. And then here's 2. It's going to be a lower effective stress condition. So that's going to be now overconsolidated. The clay will be overconsolidated because it was at a higher effective stress here in condition 1 than it is in condition 2. So the soil has been unloaded. One thing that can be a little confusing is that fluctuation of the water table above the ground surface does not change the effective stress or cause overconsolidation. So in the condition up here, the total unit weights have stayed the same, so the total stress is the same, and the groundwater table is fluctuating within the upper soil layer. If we have another condition where we have clay, let me write that in, like here's some clay, and say it's in a lake and the lake level rises, and we're looking at the stress condition of the clay under the higher water table. Well, now the total stresses change. All right, recall that total stress in the clay always has to be found by integrating from the upper surface that makes contact with air. That upper surface might be soil, it might be water. In this case, we have to include all of this water as part of the total stress at this point down here in the clay. So we get, this is the total stress for condition 2, because the water table is higher, the total stress is higher. Here's the total stress for 1, lower, so the water table is lower. Then here's the water pressure for case 2. Notice that they're the same as the total stress up here above the ground surface within the reservoir or the standing water. Here's the water pressure for case 1. Still, it's the same in that region. Okay, and then if we do the effective stress is sigma V naught minus U, and it turns out that the horizontal distance between sigma V naught 2 and U2 is exactly the same as the horizontal distance between sigma V naught 1 and U1 at every depth. Therefore, you get this green line for the effective stress, and they're the same. Sigma V naught 1 prime is equal to sigma V naught 2 prime. So like tidal fluctuations, anything like that does not change the effective stress in the soil. It has to be fluctuation of the water below the ground surface. All right, another cause is secondary compression or aging. And recall, secondary compression is this process where soil continues to reduce volume slowly over time, even if there's no consolidation happening. It's caused by electrochemical changes, biological interactions, all of the factors that cause sediment to become sedimentary rock are at work here in secondary compression. So let's say that we had a soil that was normally consolidated and we loaded it, and then it reaches this point and its consolidation is basically done. But then we go through this secondary compression phase that I'm drawing slowly. And this is log time on the x-axis. One thing with consolidation, always be sure to look at what the x-axis is, log time and log sigma v prime. It's easy to get those things confused, so be careful about looking at that. So the slope of this line happens to be called C alpha, secondary compression index. We won't really get into that in this class. All right, but if we look at what's happening here, this was a normally consolidated load stage, so the y-axes are the same. So we're starting right here, we're loading down the normal consolidation line, and then here's the end of loading. We're not adding any more effective stress anymore. We've reached this point right there. Now we're coming down the secondary compression line. So the void ratio is decreasing and the effective stress is staying the same. Well, we previously said that soil that's on the normal consolidation line is normally consolidated, and soil below the normal consolidation line is overconsolidated. So secondary compression causes overconsolidation. And in fact, you can see, let me see if I extend this down a little further. Like if we were to start at this point now and load the soil further, we would have to load along the C sub R line, a little slope like that, until we reach back to the normal consolidation line, and only then would we start going along the C sub C line in the normally consolidated region. So that means the soil is in fact over consolidated.